Hello, everybody. Good morning. It's so great to see all of y'all for this special edition of Science on Saturday. I recognize many faces, so it's glad to see that y'all were able to come here for this special Fusion Energy Week version of it. Um, as you all know, we usually have these in January, February. This was the first time I've been able to come in my Vespa to Fusion Energy Week. I gotta say, Januaries and Februarys are not Vespa weather. But welcome everybody for this hybrid edition. As I mentioned, this is Fusion Energy Week. This is something that we're launching. It's a grassroots effort across the country and actually the world to publicize fusion energy, the great work that's being done both here in the US and abroad. And so there's several events locally happening in all these places that you see in the map, but there's also several events that are virtual. So I do invite all folks to go into the website, fusionenergyweek.org, and find all of the great activities that are happening all throughout the country and throughout the world, including those virtual events, virtual tours of TAE, UKAEA, D3D, including several other things. But the folks here in person know know what's out there. And today we've got plenty of bagels and donuts and coffee for all of you all. So please feel free to take as many as you want. It's a cozy event today. So once again, what most of you saw at the beginning of the year, we're back in person. Masks are optional. And thanks for for your patience in entry. I think today wasn't that bad. Please hold. Oh no, we don't. We talked about this. You're okay with taking questions live? Yes. So our speaker is going to pause several times throughout the talk, and we're going to welcome questions throughout there, and we'll let the Zoom I'll keep track of Zoom, and Zoom participants are also invited to ask questions if that's okay, and I'll be taking care of that, and we're going to be recording the talk. So Harry, please help me out with this. Okay. So today, it's our pleasure to have Dr. Greg Hammett give a talk on Lyman Spitzer's legacy of innovation in the quest for fusion energy. Dr. Hammett is a principal research physicist here at PPPL and a lecturer in the Department of Astrophysical Sciences in the program in plasma physics at Princeton. He specializes in computational and theoretical studies of the complex physics of plasma turbulence. He and his collaborators developed computer simulations of tokamak plasma turbulence, which are successful in matching the core plasmas of a wide range of experiments. Their present work is on improving the accuracy of such simulations and extending them to a wider range of plasma conditions in a way to suppress the turbulence loss of heat from a plasma, which could lead to a more economical fusion power plant. Dr. Hammett received his BA in physics from Harvard and a PhD in astrophysical science here at the Princeton University. And just as an anecdote, when I came here 11 years ago, I audited his turbulence class and learned so much during the class. So thank you for opening that class up for beyond grad students. As always, tradition started by the late Ron Hatcher. We have 3 questions for our speaker before we begin. So the first question, what got you inspired? How did you get into the field that you're doing?
So I was always interested in physics and math as a kid, watched a lot of Star Trek. I grew up in the middle of the Apollo moon mission, so everybody was interested in those types of things. But I graduated from high school in 1976, and that was the middle of what I'll call the first energy crisis. Many of you will remember. And so that got me interested in alternative energy, and fusion sounded like something that would combine my interests in physics and something that might be useful someday.
And so the second question, who in your life, a teacher, a professor, inspired you when you were growing up?
Yeah. So I'll mention two. One is my father. He was an Air Force fighter pilot. He didn't graduate from college, but he was always reading and working on engines. And he was the first person to explain the Heisenberg, or tell me about the Heisenberg uncertainty principle. Nobody can really explain it, but he told me about it. And then the other would be Paul Bamberg, who was a professor of mine in college, who taught me a math and physics course. And that's where I first saw that is really powerful math that you can use and apply to physics in a rigorous way.
Fantastic. And when you're not doing all of what I just described in that bio, what do you like to do?
Oh, what do I like to do? Try to get some exercise, do some biking. I love, my wife and I love live music of all sorts. I'll go to concerts, jazz, classical, bluegrass. I like a lot of music.
Fantastic. So please help me in welcoming Dr. Greg Hammett.
Right. So I'm going to tell you about Lyman Spitzer, some of the early history of the lab, and kind of a legacy of innovation that he started and I think has continued in the quest for fusion energy here and around the world. There will be a copy of these slides on the Science on Saturday website, so you can look up some things there. Right, so this is an outline. The talk is kind of an informal history of early PPPL research, the Princeton Plasma Physics Laboratory, 3Ps. I want to tell you a little bit about some of the history of Spitzer's big ideas and innovations. And we know him, yeah, so he was both a famous astronomer and a pioneer in plasma physics and starting this fusion lab. I want to show you a fluid picture. So he invented something called the figure-8 stellarator and then some variations of it. And I want to show you a fluid picture of the trick for how the figure-8 stellarator works. What was the secret behind how it worked? And the basis for later stellarators. And then I'll go on to talk about some things that built on that, some of the advances in our field at this lab, and some continuing innovations at PPL and elsewhere to improve fusion energy concepts. Including, there's kind of been a renaissance of the stellarator. So Spitzer invented it in 1951. It kind of was abandoned in the late 60s as everybody switched to the tokamak approach. But there's been a renaissance of the stellarator, and I'll explain to you some of the improved ideas for that. I should mention that when I was a grad student here in the 80s, I saw Spitzer a few times at lectures, seminars. I never met him personally, although I talked to people who did. Russell Culsrud, Tom Stix, they told us lots of stories about Spitzer. And we have in the audience somebody who was hired at this laboratory in 1964, so 60 years ago. Dr. T.K. Chu is in the front row, and he was hired by Spitzer to work here. But I'll pass along to you the kinds of things that I do know. So here's a picture of Spitzer, probably from the 1940s. He was born in Toledo, Ohio, and grew up there, I believe. He went to Yale and then Cambridge and came to Princeton for his PhD, all places you have heard of. After that, he was a professor at Yale for apparently just a few years before World War II started, and he switched to work on sonar during the war. Soon after that, he became chair of the Princeton Department of Astrophysical Sciences. When he came, it was called the Department of Astronomy, but he was instrumental in changing the name later to Astrophysical Sciences. You can see that he was chair for a long time. Here's a picture of Lyman Spitzer from Life magazine. So Life magazine was a very popular magazine back in the day. And we've got a lot of older people here who know what he's holding in his hand, right? But the younger people have no idea what he's holding in his hand. It's a very powerful mathematical instrument called a slide rule, and you should look up a slide rule and learn how they try to get one. It gives you an intuition about how multiplication works and how numbers work. It's a great instrument. But this picture appeared in Life magazine in 1948. Life was kind of, I don't know, the Facebook of and the Instagram, and what are the others? The Twitter of the U.S. for well over 50 years, 60, 70 years. It was an extremely popular magazine that maybe a quarter of Americans would see. And it chronicled all stages of life, all kinds of things going on in the US. And so they did movie stars and regular people, and even had articles about famous scientists. Here's a picture of Lyman Spitzer from 1961, when he was the director of the Plasma Physics Lab. So he's a little bit older here, you can see. All right. And there we go. So in 1946, while he was still at Yale, he wrote an article to propose putting telescopes in space. This was an amazing idea for 1946. And he wrote this, it was a report to the RAND, or for the RAND Corporation, called Astronomical Advantages of an Extraterrestrial Observatory. It's essentially he proposed the Hubble Space Telescope 60 years before it started full operation. 1946 to 1996, 50 years. Yeah. So he's not the first person to propose putting a telescope into space, but he was the first person to say it really was possible, that we now had the technology to make it work, and that there were good reasons to do so. And so he made the case that you could see better if your telescope was above the atmosphere and wouldn't be affected by the movements of the atmosphere, the turbulence that goes on the atmosphere, that for high power telescopes makes images a little blurry. It's twinkling kind of effects. And also that you could see ultraviolet and infrared better from up there. So there are some websites here for NASA and another one that kind of document the big impact that Spitzer had in proposing and pushing for many years, helping the team develop the proposal and actually build the Hubble Space Telescope. So the Space Telescope was launched in 1990, and some of the older ones will remember that it did not work at first. They launched it, they turned it on, and the images were all blurry because the mirror had not been made to the right shape. It was made very precisely, but precisely to the wrong shape. And this allowed them to figure, it was in low Earth orbit, and the space shuttle was able to go up and rendezvous with it and install essentially contact lenses to correct what it was seeing. And so in 1995, I'm not sure I had that date right. It might be 93. I'll have to double check. They got the optics fixed, and they started to get great images. NASA couldn't name the Hubble Space Telescope after him because he was still alive, and they have a policy not to. But later, there was an infrared space observatory that was named after Spitzer. Here's one of the most famous images in astrophysics that came from the Hubble Space Telescope, the Eagle Nebula, sometimes called the Pillars of Creation. These are gas pillars in what's called a star-forming region. Well, most of my talk is going to be about fusion. And so most of you know, but to say, fusion is fusing together light isotopes, light elements to make heavier elements. And if you fuse together very light isotopes, you can release energy. Or if you break apart very heavy elements, you can release energy. So breaking apart the heavy elements is fission. Fusing together very light elements is fusion. And the isotopes that fuse most easily are deuterium and tritium. And this is, the sun works by fusing together hydrogen and various isotopes in a somewhat complicated cycle, but it has, a billion years or billions of years to burn its fuel. So it doesn't want to burn its fuel too fast. We can't wait that long. And so we want to use deuterium and tritium, which fuse much faster than hydrogen. And this is the main reaction, is that if you slam together a deuterium nuclei and a tritium nuclei, they will form a compound nucleus that then decays into a helium nuclei and a neutron. You'll see that we started off with 2 protons and 3 neutrons, and we end up with the same 2 protons and 3 neutrons, but in a different arrangement. And if you measure the mass of deuterium and tritium, and you measure the mass of helium and neutrons, you'll find that there's some missing mass. And you use these things way less than what they were made of. It's not very much, it's just a little bit, but the E = mc² formula will tell you how much energy that missing mass gets turned into. And it gets split between the neutron and the helium into 3.5 mega electron volts for the helium and 14 mega electron volts for the neutron. Now this is great, it releases a lot of energy, but the challenge is that this ion is positively charged, that ion is positively charged, and so they repel each other unless you slam them together with extremely high energy, unless you heat up the fuel to high energy so that in their jostling around, they occasionally run into each other close enough with enough energy that they can overcome the repulsive force and get close enough that the nuclear reaction takes over. So we basically have to heat plasmas up to 200 million degrees to make this reaction feasible. So 200 million degrees is about 20 kiloelectron volts. So if you work out the ratio of that to that, you're getting a gain. It's a huge gain in energy. It's 440 times more energy out than you put in the energy of these 2 particles. Now that's neglecting all the losses. It takes effort and some inefficiencies to heat up this plasma to get it that hot. But in the raw reaction, there's this gain of a factor of 440. And the other challenge is we have to make this plasma that's 200 million degrees, and it can't be in contact with any physical object because it will, any normal object that we would consider that's at room temperature or even as hot as an oven or as hot as the blast furnace, those are still really cold compared to 200 million degrees. And so there are 2 main approaches to fusion. One of them uses magnetic fields to keep this hot plasma away from any metal walls. And the other approach uses lasers to try to very quickly heat up deuterium and tritium, and before it has time to fly apart, that it will undergo some fusion reactions. Right. And the reason we're interested in this is that it doesn't make any carbon dioxide. And there's enough lithium in the sea. It turns out in the process of all this, you need to use lithium in the fuel cycle, but there's enough lithium in the sea to power the world's energy needs for 30 million years. If we can get it to work, it'll be really nice. Okay. So here's a 1-slide kind of timeline of how Spitzer got into fusion and what his interest is. He was an astrophysicist, but during the war he had worked on sonar, and he was that was World War II. Then in 1950 the Korean War started, and people were worried again. Lyman Spitzer and John Wheeler started. They both had worked. John Wheeler had worked on the Manhattan Project during World War II, and they both felt a sense of duty to try to do something to help. And so they started talking about a theoretical program at Princeton studying thermonuclear explosions, a hydrogen bomb. Now, as they were starting to do that, in March of 1951, on March 24th, it was on the front page of the New York Times that President Juan Perón of Argentina claimed that his German scientist, Ronald Richter, had produced controlled fusion energy in a lab. So it made a big splash. It was on the front page of the New York Times. But this was quickly dismissed by a lot of people that as being unlikely, and it was later shown to be bogus. And Spitzer, I'm sure, also thought it just didn't sound right to him. But it got Spitzer thinking on the Aspen ski slopes. He was on vacation when this happened. If you wanted to do fusion, how would you do it? So bad ideas can sometimes still lead others to, try to find better ways. Spitzer had a background in the necessary area. He had been studying hot interstellar gas and plasma for several years, and he had recently heard a series of lectures by Hans Alfvén on plasmas. Alfvén later got the Nobel Prize for his work on plasmas. And Spitzer knew that a simple toroidal magnetic field, I'll show you an example of one in a minute, could not confine a plasma. He knew that there was a problem with that. And so the story goes, and maybe part of it is apocryphal, that on the chairlift rides up, up the ski slopes, during his vacation, he invented the tokamak, which is what is currently the most successful fusion device. It has the best performance. And it was later invented in Russia by Igor Tamm and Andrei Sakharov. Sakharov is another famous, both Igor Tamm was his thesis advisor. Andrei and Sakharov is also famous. He's kind of the father of the Russian hydrogen bomb. But he later became a Soviet dissident. He protested for more freedom in Russia and was a famous dissident. So even though Spitzer, the apocryphal story is that he invented it, that he also dismissed it because it wasn't a steady state approach. And somehow during his ski lift, he came up with the idea of twisting a torus into a figure eight. And one of my goals is to explain to you why this figure eight concept is so important and how it works. Whether or not he invented the tokamak and dismissed it, that might be apocryphal, but it is true that on the ski lift, during his ski vacation, he was thinking about and came up with the idea of the figure eight stellarator. Okay, so that was in March. On May 11th, he went to a meeting with the Atomic Energy Commission to describe to them his figure eight concept, and he went with some people from Los Alamos who had thought of another approach to fusion. They both made their presentations. The very next day, on May 12th, Spitzer submitted his proposal to the Atomic Energy Commission to build a figure eight stellarator. He must have been working on it. So I've seen it, and I'll show you the cover page. It's something like 40 pages long. So he must have been working on it before. On July 1st, he got $50,000 for the first year. That was quite amazing. So May, June, July, in a month and a half, he got $50,000, which today would be equal to $600,000. So you can see how rapid they were able to get things done back then. And this is a picture of a demonstration figure eight stellarator. So it's basically a tube with copper coils wrapped around that carry a lot of current, and that causes a magnetic field inside. This is kind of a giant solenoid wrapped onto itself that's twisted into this figure eight shape, rather than just being a simple oval or a racetrack. So in the lobby, you all saw the sister of this device, which was the racetrack shape, kind of straight sections and then simple curves. You'll also notice that on the edges there are helical coils in the curve sections, and that's really crucial to what I'll talk about. But we're going to focus on the figure eight. Yeah, so this is Spitzer's original proposal. You can see that it was originally secret, confidential. And later in 1958, so this was in 1951 when he proposed it. And then the fusion program was declassified in 1958. It was part of Eisenhower's Atoms for Peace initiative. And in 1958, there was a big conference in Geneva. And it was a huge conference. There were thousands of people there. And it wasn't just fusion, it was a lot of fission exhibits were there as well. And you can kind of see old newsreels. If you go on the internet and search, you can find old video from documentary newsreels that were filmed at the event. Yeah. So July 1st, 1951, Project Matterhorn officially begins. And it was divided into two sections. There was section S, headed by Spitzer, studying the stellarator concept. Whoops. And section B, headed by John Wheeler on the weapon, on explosions and weapons side. Project Matterhorn name was recommended by Spitzer because he said the work at hand seemed difficult, like the ascent of a mountain. The stellarator, though, was named by Wheeler, who called it a star. He said it was a star-making machine, and so we'll call it a stellarator. An interesting side note about Spitzer is that he was a very serious mountain climber. There's even now he endowed an annual award for the American Alpine Club called the Lyman Spitzer Cutting Edge Climbing Award. Now, he himself was Lyman Spitzer Jr. I think he named this award after his father when he endowed it. Yeah, he did a lot of technical climbing up the cliffs and all that stuff with ropes and all that stuff. And he once, as I noted down here, he once climbed the outside of the Graduate College Tower. So the Graduate College Tower is one of the tallest towers around. You can see it from miles away. It's over near the golf course in the center, on the edge of Princeton. And one Saturday morning, Spitzer decided to climb the outside of the tower. I hope he was using his ropes and stuff. But the police were called, and the police show up, and they are waiting at the top of the tower to arrest him once he gets there. And Spitzer finally gets to the top, and then he tries to persuade them that he's not a crazy person, that he was a professor at the university and that it was okay for him to do this. Now, why he thought it was okay to do this, I'm not sure. But there was a big argument. The police wanted to carry him off to jail. But he said, well, just call the president of the university. He'll tell you who I am and that it's okay. So they called the president and confirmed that he was a professor, and the president said, please don't arrest him. But the police were very upset and asked the dean to write an official letter of reprimand in his file that told him that he was not allowed to do this anymore. Here is the Model A stellarator. Model A was the first one to test out his concept. They started the program in 51. It started operating in 53, a year and a half or two later. And it showed that the Model 8, that the figure 8 could make a plasma much more efficiently than a regular just loop of magnetic field. It was much more efficient to twist it into a figure 8. There's some interesting stories behind this. There were two professors in astronomy, two full professors in astronomy at that time, Lyman Spitzer and Martin Schwarzschild. They were both theorists, but they were good friends. And so Martin Schwarzschild helped Lyman Spitzer. They were sitting on the floor of a rabbit hutch on the Forrestal Research Campus, winding copper wire to make these coils, to make the magnetic field. So even though they were theorists, they got their hands dirty. They were very enthused and wanted to get this done quickly. They did have some help. So there were professors in the engineering department who helped build the power supplies and the vacuum equipment. Martin Schwarzschild. Some of you might know the name Schwarzschild from black holes, the Schwarzschild radius. And so That was not Martin Schwarzschild. It was his father. Interestingly, his father, Martin Schwarzschild immigrated from Germany, but his father was in World War I and died of some, while he was in World War I, in the trenches of World War I. You've heard how difficult the trench warfare was. But during World War I, he was writing these scientific papers about black holes and things like that. Really, really interesting. This picture, you see that Lyman is much older than he would have been in 1953. This picture was taken in 1980, is that right? 1983, just before this machine got sent off to the Smithsonian. So it was valued as a historical object. Right, so I've mentioned this, this figure 8 concept, and we're going to try to talk about why it's advantageous. Okay. I'm just going to tell you about some properties of particles in magnetic fields. And I'm not going to try to derive or go through the equations to derive these, but I'll just say that when there are particles, charged particles, electrons or ions in a magnetic field, they get trapped by the magnetic field. They execute these small gyrations around the magnetic field if the magnetic field is pointing in one direction, but they're free to move along the magnetic field back and forth. And to give you a sense of scale, this distance is typically for ions is maybe 3 millimeters. So this is a pretty small distance for a strong magnetic field in fusion conditions. So we need to keep this hot plasma, an ionized gas, away from any solid wall, because it would melt the wall and it would cool off the plasma. The plasma wouldn't be able to get hot. So people wanted to use magnetic fields to do that. But the problem is that the particles can freely stream along the magnetic field and they'll run into a wall somewhere. And so people thought about, well, let's bend this magnetic field into a torus, into a giant donut. So here's a magnetic field that goes around like that. And to lowest order, it works. To zeroth approximation, if you follow a particle gyrating around the magnetic field, it mostly follows the magnetic field as it curves. Okay. Now, it turns out that there is a weak drift. You'll see that it starts off centered around the magnetic field, but by the time it gets over here, it has drifted down a little bit. And most people focus on that effect to explain the advantages of Spitzer's figure 8 stellarator. I'm going to take a little bit different approach and think about the plasma as a fluid interacting with the magnetic field as a fluid. You can see that the particles kind of are gyrating around a magnetic field, and it turns out that a plasma, and it's electrically conducting, so the electrons and ions can move around freely. They strongly interact with the magnetic field, and they kind of move together because the particles are trapped to the magnetic field, and the particles can have a pressure. You can have just like gas pressure, there's a plasma pressure. And so the particle pressure can impact the magnetic field. On the other hand, magnetic fields also have pressure. You've all played with magnets, on your refrigerator or toys, or there's some ultra strong magnets, and when you have the north to north or south to south, they're repulsive, and there's a pretty strong pressure keeping them apart. So magnetic fields have a pressure. And that's going to be a key part of what we're going to talk about, thinking about this as a fluid. Okay, but I need to work up to that. So I'm going to do a few steps to work up to that. So in introductory physics, at least at the college level, everybody works out what the frequency of a pendulum is. If you have a rod or string and a mass on it, and you have it swing back and forth. A classic problem is to understand what is the frequency of the oscillation. So one can work it out fairly straightforwardly. if you have an object of mass m on a rod or wire of length L, or there's a force due to gravity. The force due to gravity is going to be the mass times the gravitational acceleration, which is 9 something meters per second at Earth on the Earth. And so that gives a force that's downward, but you'll see if the pendulum is not exactly vertical, if the pendulum is off to one side, then downward has a component of the force that's in this direction. So if the pendulum is out of place, it's going to feel a force that's going to bring it back. And that force is going to accelerate the mass, but then it'll overshoot. And on the other side, it's going to slow down because gravity is not going to pull it back. And so the pendulum, swings back and forth. You've all seen this, and this is my sample pendulum as it swings back and forth, right? Interestingly, the frequency that you can work out from this does not depend on the mass. The frequency turns out to be the square root of g divided by L, the acceleration constant divided by the length of the pendulum. Whoops. It doesn't depend on the mass because we've learned about gravity that heavy objects and light objects fall at the same rate. They accelerate at the same rate. So it turns out that the mass cancels out of this problem. But it gives us a frequency that depends on the gravitational acceleration and the length. So a longer pendulum will have as I make L bigger, this gets smaller, and so the frequency will drop. Yeah. Now, and then you can work out, the mathematical equations for that, and you can show that, for example, the position of a pendulum will have some constant times cosine omega t, where omega is the frequency, t is time, and then there's also another term. When you do these types of problems, you get cosine and sine parts of the solution, but it doesn't change the nature of the solution, so I'm going to ignore that. This is a possible solution. There are other solutions too. Okay, you've all seen pendula, right? No big deal. Well, what about an upside down pendulum? What if I try to balance a pendulum on the top? And we all know that if I try to balance a pendulum, upside down, it's eventually going to fall, right? I can try to be very, very precise, and I might get it to stay here for a second, but then it's eventually going to fall. So an interesting question you can work out is what's the rate at which it's accelerating? There's an instability, an exponentially growing instability that starts slow at first, but gets faster and faster as it falls to one side. So how does one work out a formula for that acceleration rate? And a trick is that an upside down pendulum, this can't be a string. It has to be, some kind of rigid rod to keep it from just falling straight down. The trick is that this upside down pendulum is just like this, but it's kind of like the length is negative, right? So I start here and I can make it a shorter and shorter pendulum, and then it comes out the other side with a negative L. And so this is a pendulum with a negative L. Everything else is the same, and so this formula for the frequency, you would think that would work, but now L is a negative number. It's minus times the absolute value of whatever L is here. When I take the square root of a negative number, I'm going to get an I. I'm told that kids in elementary school or maybe junior high will learn that the square root of 1, the square root of -1 is defined to be an imaginary number, I. And I has this property that this imaginary number I has this property that when you square it, it gives you -1. And so that's how how this formula works. So the formula for the frequency is I times the square root of this. So it has the same scaling with the acceleration of gravity and the length of the pendulum as the frequency does, but it gives rise to an instability, to a growth rate. I call it gamma here, a Greek letter, instead of frequency omega. So it turns out that you'll find that the position as a function of time for this inverted pendulum is some initial position times e to the gamma t plus another term that's related to that missing term. That this is a possible solution, but there are other possible solutions that in the long run, this is the dominant solution. It's exponentially growing. Okay. You kind of intuitively know that an upside down pendulum is unstable. Physically, it has these rates. And this turns out, this exponential growth is a common, is an interesting phenomena. I wanted to comment about the units of this. I said that G is at the surface of the Earth is 9.8, is that right? 9.8 meters per second per second. L has units of length, meters. So G over L doesn't depend on meters anymore. It only depends on per second per second. So per second squared, but I take the square root. And so frequency has the units, the dimensions of per time. So when we multiply it by time, we get a dimensionless number that we can put inside a cosine or sine formula. Okay. I was going to show one more trick. Kind of intuitively, you understand that this is unstable, but let me show you a trick. Some of you know this if you've had calculus, but there is a famous formula by Euler, Euler's formula, that says that the exponential of an imaginary number times some coefficient, how in the world, it's peculiar enough to take the exponential to a 1/2 power. And we understand that that's a square root, but what does it mean to exponentiate something to an imaginary number? And he worked out the formula that it can be written as a real part and an imaginary part. The imaginary part is always multiplied by I, and so it's a cosine and a sine. And you'll see that this cosine omega t is the real part of this e to the I omega t. So in this formula, if I replace, for this case where omega was was an imaginary number, if I plug in omega is I gamma into this formula, so I'm going to replace omega here with I gamma, and then I times I is, I got it backwards. Yeah, so there are two solutions. The square root of -1 is plus or minus I. I forgot about this. I'll have to correct the slides. So the square root of -1 is I, or it's minus I. Both solutions are equal. There are multiple solutions to this equation. And so if I plugged in minus I here, then I times I is negative, and it cancels the other negative. And so in the end, you get an e to the gamma t. Okay. Right. So these are pendulum examples of another type of phenomena, this time in fluids. So if you have a density stratified fluid, if you have say, salt water with fresh water closer to the top, so you have a gradient. You have denser fluid on the bottom and lighter fluid on the top. It turns out that there are stable oscillations in this type of fluid. And these oscillations will, in the right set of parameter regimes, the right wavelength of wave, they will oscillate with a frequency that is the square root of G over L, just like the pendulum. It's just that L now is the scale on which the density of the fluid is varying vertically with height, y. While here L was the length of a point for a point particle on a pendulum. Okay. This kind of thing happens sometimes when you have, say, a river flowing into an ocean. But there are also times where you can have fresh water flowing into salt water. There are underground rivers that can come out into the ocean below the surface. There are also funny things that happen with icebergs and ice sheets as they melt in the ocean. And in this case, where you have a heavy fluid on top of a light fluid, this is going to be unstable, just like the inverted pendulum was unstable. Okay. And so it's called the Rayleigh-Taylor instability. And what happens is that a convection cell gets set up where heavy fluid falls in some places, light fluid rises in other places to replace the heavy fluid, to kind of keep this incompressible motion. It takes energy to compress water particularly. So it's a motion that doesn't compress the fluid, but while taking the heavy fluid from the top to the bottom. Technically, if you had no perturbation, it was exactly uniform, that would be like a pendulum that was exactly vertical. But any small deviation is going to be unstable, and microscopic quantum atomic level fluctuations will grow rapidly. Exponential growth is very rapid and will rapidly drive an instability here. Yeah. So I love this stuff, and understanding it from all these different viewpoints, I think, is really cool. But in a few minutes, I'm going to start to accelerate. Okay. Yeah, exponentially, yes. So why this? Now we get to why is a simple magnetic torus unstable? And the reason is that it is like this inverted pendulum or a Rayleigh-Taylor instability. And so I want to show that. Let's say we have a magnetic field that goes around in a circle. It's a torus, it's a donut. Okay. We have some plasma, there's a vacuum vessel here and coils that made the magnetic field, et cetera. But this pink stuff is the plasma. It has a pressure, and it has mass. It's heavy. The magnetic field is confining the plasma away from the wall. The magnetic field is going around in a circle. There are particles that are gyrating around the magnetic field and trying to follow it as it curves around. And that can only happen if there's some kind of pressure pushing on the plasma to keep it from, instead of going straight and hitting the wall, to make it curve around like that. So there's this magnetic pressure pushing back on the plasma pressure. But the magnetic field has pressure, but it doesn't have mass. It's like a light fluid. This is a heavy fluid on top of a light fluid. As these particles are going around this curved magnetic field, they see an effective centrifugal force. You've all done roller coaster rides or amusement park rides or driven your car around a curve and felt centrifugal forces. So as you curve in one way, you feel a force that's outward, as if you wanted to go straight. You can work out the magnitude of that acceleration, the effective gravitational acceleration, and it's v squared over r, where v squared is the velocity, v is the velocity of a particle going around this circle, and r is it's called the radius of curvature. If you were to imagine a big circle, it's the radius of that circle. So a small r would be this one that curves quick, and then a larger r would curve more slowly. So this is a heavy fluid on top of a light fluid. It's just like this situation, and it's going to be unstable with a growth rate that is square root of g over L. But now g is this effective g from the centrifugal force. And L is kind of the scale on which the mass of the plasma is varied. You have a high mass density in the middle of your machine and a low mass density at the edge. And so the growth rate is square root of g over L. I plug in this formula for g, and it's the typical velocity of a particle divided by this something of dimension of length. Yeah. Now, you might think that this is just kind of an analogy to this case, because there's no gravity in this situation. It's a centrifugal force from going around a circle. But Einstein taught us that there are deep connections between gravity and acceleration in moving, in accelerating frames of reference. And so this is really a much better analogy than one might think. I'm going to stop here and ask questions. Are there any questions that anybody has? So, particularly on these last few slides, was there a step that maybe didn't make sense to you. If you have a question, probably somebody else has the same question. So feel free to ask if you want.
Folks online, they can raise their hand.
Yeah, yeah.
Folks online can also put it in the chat.
Could you go to the next slide where you're talking about the analogy with the
Or
actual
this
plasma?
one?
Yeah. So isn't it true that the magnetic field toward the center of the torus is actually much stronger than on the outside?
Yeah.
And just wondering if the analogy still holds with the ratios of the pressure and the way you're describing it, since kind of at that point it would, that lighter fluid would be on top of the heavier fluid in the plasma.
That's a very good point. And so I overlooked this. This side of the plasma is stable because you have a light fluid on top of a heavy fluid. And so this is the part that will show instabilities growing up fast. This will be the stable part. And that's actually key for my next slide. So let me go to the next slide. So this was Spitzer's trick, was to twist an oval magnetic or a donut magnetic field into a figure 8. And let's follow some magnetic fields and see what they do. I've got 3 magnetic field lines. A blue one, it goes around the torus, it comes back here and it comes back the other way, right? You'll notice that the blue line closes on itself. But you'll notice that over here, over here, the blue line is on the inside of the plasma. If we think of the green line is the center. This is the side that where the centrifugal force is outward. And so this would be unstable here, and this would be stable. But if I go around to this side, now the blue line is on the outside. The centrifugal force is in that direction, outward. And so the blue line is unstable here. So the blue line now sees alternating centrifugal force. It's outward on this side, inward on this side, and it's stable. For the yellow line, the yellow line is unstable here, but stable here. And so as particles go around, they see these alternating forces, and it cancels, and this is, in principle, a more stable configuration. It turns out it's not. Yeah, this helps a lot, but as you ramp up the pressure in the plasma, this can go unstable too. But at least for very low plasma pressure, this is a stable configuration. So I was just going to do a demonstration of this, a quick one. And you can do this with a hula hoop, but it's not as heavy. And so here's my inverted pendulum. Here's a normal pendulum, right? The mass is hanging from something, and try to do this. And so it has some frequency of oscillation. But if I try to have the inverted pendulum, this is going to be unstable. It's going to fall off one way or the other, right? I do this better. But if I spin it, it doesn't fall over. It's quite stable for a pretty long time, right? You've all played with tops and spin coins, and this is the same thing, just a larger size. So I wasn't sure if it would work on a carpet, but this works just fine. Yeah, so that's an illustration of how Spitzer's stellarator, the figure 8, makes it stable. Okay, I'm going to pause again. Are there any questions about somebody else about these last few slides?
When Spitzer came up with this idea, did he think in terms of, was it just intuition that would happen, or was he really thinking of the math, up on the ski slope, that this would happen?
He had great intuition. He had a year or two before heard this set of lectures on how plasmas behave by this astronomer Alfvén. I think he was thinking in terms of single particle orbits mostly, how particles move in a magnetic field. There's a next step, is that it turns out that the ions drift one direction, the electrons drift the other direction, and that separation of charges leads to an electric field, And that electric field drives the instability, causes particles to move outward. It causes them to feel the centrifugal force as they go around this curve. So this was the first step, and he probably solved this first step, but then it also solved this problem as well.
Yeah, it's not obvious to me how something that's unstable, so there's got to be some randomness to it. So in this figure 8, the stable part cancels the unstable part exactly, and I don't see how that can possibly be.
Yeah, so you might think that it's marginally stable. You can get slightly better stability by giving an extra twist to the magnetic field, and that was introduced in his later stellarators. But this at least got rid of the very strong instability and gave it a kind of a neutral stability that was later improved more.
So in that helical particle itself is moving, it also is generating a magnetic field in itself because it's a charged particle.
Yeah.
And you have ions, and so you have electrons and protons, which are, I would think that would drive even further instabilities.
And it does completely. So people in fusion first started to think about how single particles move, but particularly at higher pressure, at low density, yes, there are currents in the plasma, but they're too weak to feed back and affect the externally imposed magnetic field. But as you go up in the pressure of the plasma, then the currents carried by these particles will start to interact with each other, affect other particles, and they can collectively, and in fact, what they do is collectively drive this instability. So this is not a single particle effect. This is the particles interacting together in certain ways. Yeah.
Was Spitzer allowed to rappel down the tower?
Ah, that's a great question. I think he wasn't. I think he had to pack up his equipment and walk down. Yeah. Good question. Any others?
I did not see the complete analogy between your spinning loop and this. Now, in that case, the spinning loop, the motion is dictated by the angular momentum. It's a single vector in vertical space.
Right.
And this one, I do not see how can we just put them together.
Yeah. It's not a perfect analogy, maybe in that sense, but maybe it's that particles have to move quickly enough through the bad curvature, through the unstable side to get to the stable side. You know, if I don't spin this fast enough, it will just fall over to one side. So yeah, so it has to spin fast enough.
It's completely different motion. It's only a single direction vertical.
Right.
That determines.
Yeah.
In other words, you cannot bend the force that vector in space, put it on the side.
Right. And similarly, if there's a particle that's moving very fast here, there's something like an angular momentum from the fact that it's going around in a periodic motion. But yeah, it's a good observation. There are differences between that analogy and this. Yeah. Okay, I'm now going to fly through this last set of slides, and maybe I'll try to finish up in 10 minutes. We'll go over a bit, but I can take more questions later. So Spitzer kind of realized fairly quickly that rather than have a figure 8 coil, rather than make a figure 8 plasma like this, one could have helical coils that wrap around the plasma like that. And that this gives a similar twist to the magnetic field as the figure 8 and also gives stability. And then at some point, I think maybe in the 60s or 70s, people figured out that you could actually also make a stellarator with these types of coils where they aren't linked. these types of coils are kind of hard to manufacture. You have to do it in place because while these, you can manufacture each coil separately and then bring them together. There was this big Atoms for Peace conference in 1958. And it was interesting that when fusion was declassified, scientists from both sides had invented many of the same things. So they'd both invented mirror machines and pinches and symmetric toroidal devices of various kinds. But the one concept that only one side invented and the other one hadn't invented was the stellarator, was Spitzer's invention. And there's a quote here from Marshall Rosenbluth, a famous physicist, about how he always was quite amazed by Spitzer's insight, his geometrical intuition to figure this out. But he also goes on to tell a story that the Russians were embarrassed to find out that, that Spitzer had invented this and they hadn't. So they fabricated drawings for a stellarator that they claimed that they had invented as well and included it in their submission to the conference. The original plan was to, Spitzer was ambitious or optimistic about how things would go. And so, you saw a picture of the Model A, then he was going to have a small scale Model B, and then a medium scale Model C, and then an industrial scale Model D that would actually, you would put in tritium fuel to make energy. Model A showed the basic advantages of the figure 8 over a racetrack. But as they built the larger devices, they started to find difficulties, various instabilities. These collective motions of the electrons and ions interacting with each other would drive small-scale turbulence and cause particles to leave the plasma more quickly. So in the 1950s, there was a long series of different Model Bs to try out different ideas, but all at this kind of intermediate scale. You can see one of the devices back there. And he really built a very strong team of excellent scientists that contributed to the program for many years. Just wanted to point out Bob Ellis. I knew Bob and Wolfgang Stodiak, and Bob ran the experimental program at PPL for decades after this. One of the things that improves stability, we were saying that it's kind of marginally stable with this twist, is to introduce shear in the magnetic field. So the magnetic fields are not all parallel, but magnetic fields kind of are nested and they twist at different rates as you go out. This was another thing that actually Lyman invented and figured out how to put in this kind of twist into stellarators. Although they were having difficulties with the Model B series, they got good enough performance to justify building the Model C stellarator, which operated from 61 to 69. Here's a picture of it. You can see a scale. There's somebody crouching down. There's somebody else crouching down. There's somebody standing. And so Dr. Chu worked on this device. Did you work on this device? Oh, you didn't. You worked on something else. Okay. But many people did. And it showed a number of advances. It produced deuterium ions that got up to 8,000 electron volts, which is close to what you need for a fusion reactor, but the average ion temperature was only 400 EV, much too cold. And in 1968, the Russians reported that their tokamak concept had gotten to 1 keV. So 2.5 times this record value. And that was for all of the ions, the average ion temperature, not just a small fraction of the ions. And there was a big controversy about that, whether it was true. The British sent a team over with a laser to measure this and confirmed that they really did get that temperature. And so in 1969, they decided to shut down the stellarator, but convert most of this device into a tokamak, into a symmetric tokamak. Yeah. This was over in, down there, right next to your offices. Yeah. Okay. So the ST, when the CMOD, when the Model C Stellarator was converted to tokamak, they got great performance, and then there was a series of tokamaks that were built here at Princeton, and the performance was good enough. People were getting excited about it, and then in 1973, the Arab oil embargo hit. That set off the first energy crisis that lasted for over a decade. It led to large funding for alternative energy. And so they were ready with the science, and then there was motivation to build a bigger machine. And so in 1974, they started design of what was called the tokamak fusion test reactor. In 1976, construction was authorized. In 1982, they got first plasma. The main machine existed, and they were able to make a plasma. The total construction cost was about $1.4 billion. And in 1993, they finally put in tritium fuel, and eventually they made 10 megawatts of fusion power. So that was a big deal. That was a big breakthrough to make 10 megawatts of fusion power. This is the first device to really use large amounts of tritium to do fusion. And we ended up all over the newspapers. We were, on the front page of many newspapers. We were on the nightly national news. It was great fun. This room was filled with journalists. It was a really fun time. Let's see, and it was scientifically, it was a huge advance. A key parameter for fusion is what is the fusion power gain Q? What's the ratio of the fusion power output to how much heating power you have to put in to heat up the plasma? And when TFTR started design in 1975, Q was roughly 1/1,000,000. We improved performance by a factor of 1,000,000 by 1995 when TFTR got its best results. So it wasn't quite what we hoped. We hoped to get to Q all the way equal to 1, but so we needed 3,000,000. We only got it. If my goal was to get $3 million, but I only give you 1,000,000, you're still kind of happy. Interestingly, the day after we ended up on the front page of the New York Times, on December 10th, the space shuttle fixed the Hubble Space Telescope optics. And there were front page, or at least in the newspaper, in the New York Times, articles about that. So Spitzer worked on both of these things, and from one day to the next, both of his really big ideas ended up bearing fruit and showing real progress. This is just a picture of everybody was very happy when they did their first tritium shot, and it worked. That's another fun shot. I want to finish with a few slides on current progress in fusion. So my big picture, maybe 5 more minutes. My big picture perspective on fusion is that we need to pursue many energy sources. We need to pursue solar and wind, geothermal and hydro, and carbon sequestration, and maybe once through nuclear fission power. All of these have trade-offs and uncertainties, particularly when you try to go to large scales. Wind and solar are intermittent. The wind doesn't always blow, the sun doesn't always shine. And it's challenging to supply all energy needed, particularly in the long term. Yes, we need to switch to CO2-free energy sources over the next couple of decades, or dramatically reduce the amount of CO2 emission. But through the rest of the country, poor countries are going to continue to develop, and they expect energy usage to triple between now and the end of the century. So we need to continue to provide much more energy. So we need to try everything. Fusion is hard, but it's an important problem, and we've been making progress. There are a lot of interesting ideas that could make it more competitive. I'm not going to cover them all, but I'm just going to say that there are some real breakthroughs that could be made. This shows the projected construction cost for a fusion reactor as a function of the confinement time, how well we can confine plasmas. If we can improve the confinement by just a factor of 50%, we can perhaps reduce the cost of a fusion reactor by a factor of 3. So there are some big improvements that could potentially be made. And there are good ideas for how we might achieve those, things like liquid metals and the spherical tokamak, which we are doing an experiment with here, that we are upgrading its, restoring it to full capability. There are ideas about advanced tokamaks, about stellarators, advances in magnet technology that can really help a lot. I think one of the things that could help is robotic manufacturing. That could, I'll show you why in a minute. I'm going to just do a few more. This slide shows the difference between a regular tokamak and a spherical torus. And so we have a major experiment here, the National Spherical Torus Experiment, which is in the process of being rebuilt and enhanced. And it's like this, and it has certain advantages. It's able to get to pressure limits that are 4 to 10 times as much as a standard tokamak. And the fusion power goes like the pressure squared. So, you know, going up a factor 5 in pressure is 25 times more fusion power. This is a really big deal if we can make it work at a reactor scale. The stellarator is making a comeback. You know, we talked about how the stellarator was originally invented, and it was mostly abandoned for tokamaks in 1969. But this is what a modern optimized stellarator might look like. And you can see that these coils are quite complicated. And there's no way that Lyman Spitzer, with his slide rule, could have figured out how to build design this device. But we now have the computer tools needed to optimize these kinds of designs. And also maybe advances in manufacturing that can make these types of things more easily. I think that's robotic manufacturing, I think, is another breakthrough that's coming in the next 10 years, perhaps, that will help, that could help fusion a lot. The types of, there are many different types of stellarators. I've shown you some already. There is something called quasi-symmetry that was discovered in the 1980s, but the full range of possibilities are still being explored. And it was just last year that a new article proposed a new stellarator design that got extremely good confinement of particles, at least from the single particle perspective. We now understand that there are multiple classes of improved stellarators: quasi-helical, quasi-axisymmetric, quasi-isodynamic. These colors represent the strength of the magnetic field, and so you can see that this is, here the magnetic field strength is helically symmetric, here it's toroidally symmetric, here it's kind of symmetric the short way around. And each of these has different advantages. We don't yet know which of these approaches is going to be best. But we're trying to build experiments, we're trying to also develop computer codes that can really simulate these well and help us design what the next experiment is. If an experiment costs $1 billion, you want to have good computer simulations to back it up and really be confident that this is the right step to take. So this is my summary slide. I've told you some about the early history of Spitzer's big ideas for the Hubble Space Telescope, for fusion, and the figure-8 trick. And it wasn't just for his figure-8. It's kind of this main idea that you have to twist the magnetic field that has impacted all toroidal fusion concepts, or particularly stellarators. I've shown you a fluid picture to illustrate that. I told you briefly a little bit about some of the ongoing innovative work going on here and at many other labs. So thank you very much for your attention.
Thank you so much, Greg. That was excellent. We have some time for a few questions. Britt, are you? Yes. Okay. Do you want to do 1 and 2? And
Yeah.
please, can we hold for the microphone so that we can record it?
Can you
Can we
pass the-
start?
Okay, and over there.
No, with
yeah.
the white jacket first?
He raised his hand first, so we'll go with them.
Yes.
Yeah.
Can you hear me?
Yeah.
Um, I have a historical question. Do you know why Spitzer and Wheeler picked this place as a site for PPPL, and why Rockefeller University left?
I don't know why Rockefeller left. They did medical research here at one time, but in general, this area was the Forrestal campus. It might not have been named that at the time, but it might have been by 1940, by 1951. But this was in general a research campus for Princeton University. There used to be an airstrip between here and Route 1. And so the aerospace department had experimental aircraft there that would take off and they would do experiments there. There were various other research labs separate from undergraduate education that was carried out here. This is also, they could do classified work here at that time. Princeton no longer does classified work, but as you leave this place across Route 1, you'll see a old New Jersey, who are the highway police? What's their name? The New Jersey State Troopers, yes. So there's a State Troopers barrack right across Route 1, and they used to provide security for the classified work that went on here.
We'll have another one here. There's a raised hand, so can we
Sure.
please unmute while we have the in-person? Yeah, go ahead.
First of all, thank you very much. I really enjoyed the journey from why you need a kind of figure eight or rotating structure. And I have kind of maybe a suggestion for the spinning top to make that a little more. Maybe this will help. If you've seen the demonstrations before where you have a bicycle wheel, and if you hold one side, it'll just fall over. But if you spin it fast enough, it'll be stable. I think that might help bridge the gap between like when you have this fluid moving so fast that these unstable and stable parts can sort of interact.
Yeah.
But yeah, thank you very much.
Yeah, thanks. Yeah, I thought of this at just a few days ago and needed some, I tried a hula hoop, but it doesn't have enough weight. It slows down too fast. Let's go here.
Oh, but before that, Vishnu Sharma online, can you unmute?
Yeah. So the question I had was that I noticed that for the modern stellarator slide, the linked coils like seem to be very symmetric, but the unlinked coils like seem to be very like I don't know, asymmetric. Does it like form a symmetric field or like have some kind of effect that makes it kind of like better to have it be like so kind of like look so like asymmetric or like so I don't know. Yeah, why is that?
Yeah, that's a good question. Yeah, these look symmetric and this looks very unsymmetric, and the symmetry helps, but it turns out it doesn't matter what the coils look like, it matters what the plasma looks like. And do I have this plot here? Yeah. So this plasma turns out to be very symmetric. The magnitude of the strength of the magnetic field is very symmetric in a funny coordinate system that's following the magnetic field around the torus. Yeah, it's a good observation, and you have to kind of go through some heavy-duty math and computer simulations to really see it come out.
I like when it's described as plasma first, as you design the plasma first and then figure out what the coils need to look like.
Right.
As opposed to like the early ones.
Right.
So this is all really, really interesting, but one of the issues that we have with any energy system coming from coal or gas or anything else like that is the recovery of exergy, the actual work that you can get out of any heating system. Is anything being done to explore, I mean, a Rankine plant is 33% efficient. I mean, what's being done to actually recover work from the system or anything?
Yeah, that's a good question. There are kind of the standard approach would, like a coal power plant or even a fission reactor, eventually the heat gets transferred to make steam and the steam runs turbines. And there are limitations depending on the temperature of that cycle. There are some fusion concepts that will use very high temperature blankets to capture the neutron energy. And so that I think there sometimes, I don't remember the exact numbers, but maybe a cycle where it's running at 1400 C. I'm not remembering the exact numbers. I'm a theorist. But I know that people are looking at higher temperature options. And then there are really futuristic things that try to do some kind of direct energy conversion, take the charged particles coming out of a plasma, pass it through electrodes, and directly generate electricity that way. Whether or not that's really practical because the electrodes will erode over time, I don't know. But in terms of net energy gain, they're Westinghouse. They don't have the best reputation right now, but a lot of companies have done serious reactor design studies, and if we can make the plasma work out, then the energy cycle can work out as well. But certainly, if there are ways to improve that will help and help bring down the cost of electricity. Yeah, certainly 50% efficiency versus 33%. That's brings down your cost of electricity by 30% or something.
There's a question over here.
Thank you for the lecture. My question on the accelerator, for the ideal accelerator, all the particle will be accelerated without colliding with the wall and each other. So for the real practical in a lab, is that some percentage of particle that would still colliding with the wall, or everything you had to be 100%?
Yeah, a few particles. Well, every particle eventually escapes. But if we did not have a magnetic field, then a 10 kilovolt particle in the center would escape to the wall in a microsecond or less. With the magnetic field, the particles go around and around about 1 million times. I'm sorry, they about 1 million times longer. And so they'll be confined on average for about a second or a few seconds in a reactor. So we do have to worry about these particles eventually hit the wall and carry some heat, and how do we handle that heat? We don't want the wall to melt. And that's actually one of the ongoing challenges. We have some ideas to try to handle this. Liquid metals can help, or puffing in a little bit of argon or neon to radiate away the heat and spread it out over a large area rather than the particles just hitting one narrow area. There are a number of ideas being pursued. Yeah.
We have another question by Vishnu online. Vishnu, do you want to unmute?
Yeah, just a second thing. I was wondering. So like a lot of this uses like obviously static magnetic fields. I was wondering, like, is there a place where, or like, is there possibly like a scope for using moving magnetic fields, or is it like overall just like too unstable to rely on magnetic fields that move around even a little bit in order to achieve desired stability?
So you're asking about moving magnetic fields, and that is tried for some approaches called Z-pinches or reverse field plasmas. They have historically been somewhat unstable and so challenging to make them work. They do have other applications. So things called Z-pinches are used as an intense X-ray source. But there are some people looking into using Z-pinches, these time-varying moving magnetic fields. But they have to overcome some of these instability problems, find a way to stabilize them so that they can last long enough to make fusion.
The last couple of questions we have here and here.
Yeah, thanks. Can you explain how you can maintain these dramatic temperature gradients? So the plasma is 200 million degrees and the wall of the stellarator is essentially room temperature. That to me is a discontinuity in temperature. How do you maintain that?
Yeah. So yeah, a big part of it is the magnetic field acts as an insulator, and it is the world's best insulator, which is how we have actually achieved these extreme temperature gradients. But it's not a perfect insulator. Particles will leak out of the magnetic trap over time and eventually hit the wall. They usually cool before they get to the wall, so that helps. Another is that the plasma is extremely low density. So I don't know if you've ever made cheese toast, take aluminum foil and put some bread on it, put some cheese and put it in the oven. When you open up the oven, you can grab the aluminum foil with your bare hands and take it out. Because the aluminum foil is so thin, although it's hot, the energy density is not very high. And so it doesn't burn your hand. And so it's a similar thing here, that in some cases, we can handle that heat flux. But it's still a challenge. In some scenarios, the power load is, if you didn't do anything about it, it would be a gigawatt per square meter, which is something like 10 times the rocket exhaust or 20 times the rocket exhaust heat flux. And so we're using various methods to get rid of that heat before it hits the wall. Yeah.
There's a lot of research done around the world. I mean, it's truly an international operation. Any ideas of what experiments are being done around the world that you think are showing the most promise?
Let's see. So the Joint European Torus in England just shut down, but they did set a record. So it's a tokamak, like generically a tokamak. They just made 69 megajoules of fusion energy last fall. The W7X accelerator, I have a note about it here down at the bottom. So this is a $1 billion device built in Germany I think they started operation about 5 years, actually further back, 8 years ago. And they're getting good performance with these funny shaped coils, not this particular design, but generically a stellarator. And so that's been getting good performance. It's very stable. It seems to get performance comparable to a tokamak, but maybe more stable than a tokamak. And so this is very interesting. And then there are companies, various companies. So there's a spin-off company from MIT called Commonwealth Fusion Systems. And they hope within I don't remember their exact timeline, but maybe 3 years that they'll have a demonstration experiment that might make 10 times as much fusion power 10 times more fusion power than they put in to heat it up. So if that works, that will be a huge milestone in the program. And then there's NIF. So right, so I was talking about mostly magnetic confinement fusion. There's a big laser at Livermore, which last year and a half, was it just last summer?
It was December of 23, and then just recently they got even higher.
They've been able to make it more reproducible. And so they have also gotten a break even where they get more energy out in fusion than they put into the pellet itself. Now, there are all certain electrical inefficiencies in making laser power. But anyway, that was a big breakthrough for this laser approach. There's still more work to do to make that a commercially viable approach.
I think that's a great segue actually to all the stuff happening in Fusion Energy Week. Y'all, please take a look at the website. There's a tour of NIF actually. There's virtual tours of different machines. So yeah, I welcome everybody to go to fusionenergyweek.org. And so please join me in thanking our presenter today.
I'll stick around for anybody who wants to ask questions.
That's what I was going to ask, if you're able to stick around for a bit, if people want to chat. But
Sure.
thank y'all for coming for this off-season Science on Saturday. And of course, we welcome everybody to next year's Science on Saturday seminar series.